Hey folks, welcome to the last session, the 10th and last session of high performance LLMs and first principles. We have a special guest here, Sharad Vikram, who's going to be teaching us about Pallas. Pallas is a high performance kernel language for TPUs and GPUs in Jax. I'll let Sharad take it from here.
Thank you, Robbie. Yeah, excited to share some Pallas knowledge. Some quick background about myself. I'm Sharad. I have been on the Jax team for like 2.5 years. Last year or so has been spent on Pallas and kind of the material I'm showing you. I'm going to be like kind of, I have like basically a set of slides that, I think should take around half an hour. And then I have some like more interactive kind of collabs that we can go over as well. And yeah, feel free to like interrupt me at any point and ask me questions. And without any further ado, I think we can dive right into it. Cool. Yeah, so I've been on the Jax team for about 2.5 years. I initially worked on like kind of side effects, front-end transformations kind of stuff, but over the last year or so, I've been doing a deep dive into the lower level aspects of programming accelerators. And you might ask, why has the Jax team embarked on this? What justifies this kind of investment? And so I'll go over like why we've done this initially. And largely speaking, it's control. One of kind of the greatest advantages of Jax historically has been its reliance on XLA, which is a fantastic compiler, and on TPUs especially because we kind of own the entire stack. There's a lot of co-design that has gone into it, and XLA in general on TPU has achieved really good performance numbers. But if you contrast that with the outside world, if you will, on GPUs, the GPUs expose kind of many levels of entry to programming. There's high-level kernel libraries, there's like medium-level libraries like Triton, and there's CUDA-C, and then there's even PTX if you want to write that directly. Historically, that has not existed on TPU. It's only been the high-level entry point, and all of the kind of internal representations for low-level programming have been inside of the compiler. So part of Pallas is exposing that level of control to users, whether they be researchers or compiler engineers or kernel wizards. The goal is at least to just have this be out there so that people can push the frontier even further on TPUs and GPUs. Some more details are that like Jax has historically been very declarative. You write the computation you want. You don't really specify how it's executed, and a compiler does a lot of the decision making for you. It'll figure out how the memory is laid out. It'll figure out how it's scheduled. It'll figure out exactly what kernels to call and what kind of templates to use, how it'll fuse things for you. A lot of the decision making is done by the compiler. And this is really good because you can just think about the math you want to execute and the compiler will do the rest. But we're reaching this stage, especially with LLMs and large-scale distributed LLM training and serving, that we want to optimize things even more than what the compiler can do. We want to run ahead of the compiler. We want to iterate really quickly, as opposed to improving the compiler. And compilers are often, while they can do a lot, they're often slower to move than say some handwritten custom kernels. So we want to have this nice balance between the compiler and kernel writing, where the compiler, it has this like great global view. We can do all these optimizations, and there's a lot of things the compiler does really well, but we don't want to be blocked by it. So we want to provide essentially an escape hatch, where if you feel like the compiler is not doing a good job and you don't see it being able to improve fast enough to do what you want, you always have a backup plan. And that's basically what Pallas is about. So, there's other such escape hatches. Shard map is one of them. It basically says, I don't want the compiler to decide how my program is distributed. I want to write my own collectives manually. In kind of motivation and in spirit, it's very similar to Pallas, but we can talk about that at some other point if you want to. Pallas is what we'll focus on today, and that's specifically for kind of the final stage of the compiler, which is generating assembly, writing kernels, what exactly is executed on each accelerator. So why haven't we done this earlier, and what are some challenges? Well, first is that kernels are complicated, hardware is complicated, and kind of one of the best parts about XLA is that we don't need to we don't need to educate everybody on exactly how the accelerator works. It provides this like high-level math language, and all the details of the hardware are abstracted away. You don't need to think about them, and the portability of your code is like one of the huge pluses of XLA. And portability is something that it might be the first thing we can sacrifice if we're thinking about one-off bespoke large-scale training runs, because we're not going to run the same exact thing on GPUs the next day, for example. So portability is something that we often sacrifice. So, but as a result, we do also need to teach people how accelerators work to some degree, how the lower level bits work. So what is the minimal way of teaching these concepts without overwhelming someone while preserving as much of the Jax programming model as possible? So Pallas is like trying to straddle this line where we're teaching the user new things about how accelerators work, but we're not like trying not to overwhelm them with information and essentially teaching them a brand new way to write code. We want to make it as similar to Jax as possible. So what we've landed on is essentially something that hooks into Jax in a fairly straightforward way. We preserve essentially a lot of the Jax APIs, like all the control flow operations, a lot of the JNP operations that you're used to. It works well with transformations and Jax's existing machinery. And while you may write a kernel on TPU, it may not exactly work on GPU. The kind of like the differences should really boil down to hardware differences as opposed to language differences, and that's basically where we've ended up. And yeah, the big related project is Triton. Pallas is really inspired by Triton. The fact that you can have a kernel language in Python that's performant and intuitive and friendly. Triton really was one of the first to push on that on GPU. The main differences are just that Pallas is like it works on TPU. That's a big difference. And I would say it's a slightly higher. Its programming model is not exactly the same. Triton has pointers and things like that, but you won't see any pointers in Pallas. So what is Pallas on TPU like, and what does it change about the kind of current TPU stack? As I described before, GPUs have this like rich array of different levels of abstraction you can program at, but TPUs have basically looked like this. And the Jax team, in collaboration with XLA TPU, have developed Mosaic, which is essentially a Triton on TPUs. You can see that it's like not perfectly aligned with Triton's abstraction level, because in some ways it's higher level, in some ways it's lower level. Happy to go into the details later, but it is kind of this tile level programming language where some of the hardware details are exposed, but some of them are still hidden. So you're not directly writing assembly, but you do have to think about some things more explicitly. In practice, it's like basically an MLIR dialect. On the right is a very simple function. You can see your standard set of MLIR dialects in there. So we tried not to kind of invent a totally new programming language. We do have this bespoke TPU dialect. I'll get into that later. And the idea is that rather than having to write your entire Jax program again from scratch in terms of these kernels, you can embed calls to these custom kernels inside of larger Jax computations. And it's via this custom call mechanism in HLO that basically tells HLO this is a black box and it's responsible for its entire execution, but at its boundary it looks like any other HLO op. And we'll get into how to embed these into Jax later. And basically, we have our own passes that turn this assembly into, or turn this a Mosaic IR into TPU assembly, also known as LLO. And the idea there is that the compilers kind of merge at some point, where once we get to LLO, we rely on XLA TPU's existing machinery to essentially create the machine code that's run. So some of the infra across Pallas/Mosaic and XLA TPU are already shared, but the important part is that it's lower level than HLO, but kind of eventually targets the same thing. The main distinction here, like, is not super important for now, but the idea is that fundamentally the hardware in TPU, and we'll go over this later, looks like you're operating these 8x128 arrays, if you will. And all ops basically take in 8x128 arrays and output 8x128 arrays. So all problems that are larger than that have to be decomposed into many ops with different 8x128 arrays, and operations that are smaller than 8x128, you now need to think about things like padding, where you have to store a smaller than 8x128 value in this like bigger array. And Mosaic is basically responsible for that. And because Mosaic handles this for you, it basically allows Pallas to, you can think about arrays in most of your familiar shapes. You can think about things that are 9x129, and essentially Mosaic needs to worry about the padding of those extra rows and columns. Or you can think about things that are 1024 by 1024, and Mosaic will handle exactly how that 1024 and 1024 is carved up into smaller 8x128 little arrays. So the kind of hello world in Pallas, if you will, starts with you writing what we call a kernel function. It looks a little bit different than Jax functions. The first thing to note is that rather than being given Jax arrays, which you can think of as like just mutable logical like arrays, you're given these references, and references have slightly different semantics. The first is that you can see us indexing into them. That's normal, but when you index into a ref, you get out a Jax array, something that's immutable. You can then do normal things with those Jax arrays, like add them here. And then the most important and interesting thing is that you can mutate these refs. You can see that we're updating zref in place. And this is something that we don't normally allow in Jax. It's kind of like a special extension you get in Pallas. And this is a lot more close to what's actually happening in the hardware, where we're writing to memory locations and overwriting what's already there. That sort of thing is not exposed in Jax as an operation. Normally you have to do these functional updates, and then you hope that the compiler does something in place for you. Here you have explicit control over what happens in place or out of place. You can take this kernel, and then to kind of embed it in a larger Jax program, you wrap it with Pallas call. You can see here that by wrapping it in this, you get this Jax add kernel function, and this Jax add kernel function takes in regular old Jax arrays and then outputs regular old Jax arrays. So you can kind of slot this into any larger Jax program. And maybe the only important thing to note here is this out shape. We have to tell Pallas call needs to tell what the output of it will look like. So in this case, since we're just adding things together, the shapes don't change. So we get something that looks like X as its output. And that's what that zref corresponds to inside of the add kernel function. So basically, the two pieces are something that is representing the compute, aka these refs, and then something that is lifting it into a larger function that you can call in Jax. So this is kind of where the hardware details come up, and we want to learn basically the minimum amount about the hardware that we need to without that'll enable us to like write really performant and new things without overwhelming us in too many details. So on the right is basically a cartoon of what a TPU looks like. Again, this is already an abstraction. I'm hiding a lot of things that are actually happening in TPU, but this is certainly more than what is given to you in regular Jax documentation. And the idea is that there's two kind of pieces of information we are exposing explicitly in Pallas. The first is the notion that there are separate memory spaces within a TPU. Normally, we think about HBM, and that's like the conventional memory that we think about when working with TPUs. And this is the thing that's like on the order of, I don't know, 60 gigabytes or 40 gigabytes or something like that, or 16 gigabytes. It's usually in the gigabytes. VMem is essentially an L1 cache. It's on the order of megabytes. It'll be 16 megabytes on some platforms, or 128 on some, or 64 on another, but that's roughly the range it is.
So just if I could just hop in for a second.
Yeah.
This is a picture that we've looked at a much simplified version of a number of times in these sessions. So what we are showing here of VMem, SVEM, VREGs, and SREGs, we always just lump together as SRAM. And then the MXU vector and scalar compute, we've always just called compute. And then we've had HBM. So this diagram has gone from like, used to have 3 boxes in previous sessions. And now in this Pallas session, we're up to like 8 or whatever. So just going one level of detail deeper.
Yeah, so I guess we're like peeling back the one more layer of abstraction, if you will, compared to what you've seen before. So the distinction between all the memory spaces is usually like, so at least HBM, it's what you're familiar with. VMem, smaller. SMEM, even smaller. Between VMem and SMEM, we'll talk about SMEM later, but VMem is like the more important one usually, because we want to get a lot of flops We want to maximize our flops utilization, and we get that by doing lots of parallel operations, basically these big instructions. And those vector registers up there, those are the ones that are 8 by 128 that I described before. And the idea is that in order to do any operation on TPU, you need to move your values from HBM into VMem into VRegs, do compute within the VRegs, write it back to VMem, write it back to HBM. So what's happening underneath the hood in this Pallas kernel, if you just call Jax add kernel, is first we'll allocate an HBM output buffer for Z. We'll then allocate a bunch of scratch space in VMem for this kernel. VMem is basically like reset every kernel in most cases. We then basically copy HBM into VMem. We copy X and Y into VMem directly, of course, assuming we have enough space. We then, these ref read operations, that indexing actually turns what was previously refs in VMem into values. These Jax arrays are essentially VRegs. We then execute, in this case, a vector compute op, which is just adding two 8 by 128 array, adding sets of 8 by 128 arrays together. We then do a VMem store, and then we do a VMem to HBM copy. And that's basically the life cycle of a kernel, if you will. You want to start in HBM and end in HBM, usually. But in between, there's basically data movement and compute that happens in order to get the data you want right next to the compute, which is the matrix multiply unit and the vector unit. We'll get to scalar stuff later. But yeah, any questions about this picture? I guess it's conceptually, this is like the flow that happens when you call a Pallas kernel.
So maybe you can give us a sense of like what sizes this will have problems with. Will it fail when we run out of VReg, or will it fail when we run out of VMem? Or
yeah, so they're closely related. So at what point does this stop working? And the answer is, yeah, when you run out of VMem. VMem is the main bottleneck. VRegs, you can kind of, even though there's physically a fixed amount of them, you can pretend like you have an infinite amount. And the compiler will basically do register. It has a register allocation pass that basically ensures that we only use the physical amount, and any extra data we can't store in VRegs will be spilled into VMem. So really, VMem is our limited resource here. And if you try using too large sizes of this kind of op, you'll get a compiler error saying we ran out of VMem.
awesome.
Yeah. So the other thing to note that about what we're doing here is that this is really not a good thing to do. The most important thing happening here is actually the copy from HBM to VMem. This is the thing that's usually going to be the slowest here. We have, in most cases, we have a lot more flops available to us than memory bandwidth for this kind of ops. Or sorry, like we'll be able to do the compute a lot faster than these copies. So this entire op will be just bottlenecked by copying back and forth from HBM to VMem. So in general, this is not a good idea. We shouldn't block all our kernel on these copies. We want to do something a little bit smarter. And the answer is pipelining. So the first thing we'll do for this op is we'll chop up our inputs, and we'll also have like a chopped up output, if you will. And what we're going to do is we're going to do the compute while we're doing the memory copying. And it's a basic pipelining idea. So initially, we'll do the same thing we did before, where we allocate these scratch spaces, but they're kind of logically partitioned. We'll do a blocking copy of the first chunk, x0 and y0. We'll then asynchronously kick off copying x1 and y1. And while that's happening, we will do the compute for the 0 chunk. And then we'll start asynchronously kicking off the copy back from VMem to HBM. Now we wait for the asynchronous copy we kicked off earlier to be done. Then we do the compute for the first chunk. Then we wait until we're done copying the 0th chunk, and then we do a blocking copy for the final chunk. So this is in practice what most TPU kernels look like. They're a software pipeline implemented in assembly, but in this case, we want to do something like this in Pallas as well, so that while we're doing all this memory copying, we're doing compute at the same time. And ideally, we have enough compute to entirely hide all the memory copying, so that our chip is spending all its time just doing compute, and none of the memory copying will even, it'll all be hidden behind this compute. And that's what we call being compute bound, basically. Versus if we're spending our time waiting on the memory copies in each of these steps, then we're memory bound. Any questions about this? Because again, this is like an important concept for Pallas. Is this something you already covered, Rafi?
We've definitely covered pipelining and then being memory versus compute bound.
Cool.
So very, very related topics in the in the sessions before this.
So yeah, so obviously this is like a non-trivial thing to write yourself. So the question really is, how do we expose this to users? How do users write pipelines without having to like do all of this manually? Because there's a lot of steps in it. And the answer is we came up with something called block spec. It's not a crazy new idea or anything, but the idea is that it's essentially a piece of structured information that we can provide to the kernel that allows it to auto pipeline. The first thing, there's kind of two things you need. You can see in this slide that the two things we did are we carved up the inputs into these logical blocks and the outputs, of course. And then we started doing this prefetching where during essentially the computation for the 0th chunk, we have started fetching the computation for the next chunk. So we need some way of telling the pipeline what should I be copying right now on this current iteration? Essentially, what's the next iteration? What is the block that I'm going to be using in the next iteration? And that's what this index map function tells you. It basically says what is the for each iteration, what is the block needed for that? And with that function, you can predict the future. You can pass in the next iteration and figure out what blocks are needed for that, and the pipeline can start prefetching them. In practice, it turns into something like this, where you write a matmul kernel. So this is like essentially a conventional matmul kernel in Pallas, where you have an accumulator. You zero it out in the first iteration of the reduction. You accumulate into it, and then in the last iteration of the reduction, you kind of write the accumulator back into Z. And again, this is all you write these kernels as if everything's VMem already. And note that we're not thinking about pipelining at all. This is just a single iteration of compute and nothing else. And in the caller, we basically add a lot more information to the caller. The first is you specify what we call a grid, and this is basically a nested loop. So in this case, we have 3 entries in this tuple, so you can imagine it as a 3 nested loop. So the first is like over from I to M divided by Bm, and inside it's for J and N divided by Bn, to the last one's like for K and K divided by Bk. So it's a nested loop, and this kernel is running that many times in sequence. The other thing we specify is for each of these iterations in this grid, what is the block we'd like for each of our inputs and outputs. So you can see it takes a lambda, which is ijk, and it basically says, if we're in the ijkth iteration of this nested loop, which index of our input, which block essentially are we selecting? And in this case, it's a matmul. So there's kind of a standard pattern we associate with matmuls like this. The innermost grid dimension, the rightmost one, is k, and that's the contraction dimension of the matmul. So we'll be basically accumulating over that dimension. So we'll be selecting the ikth block for x, the kjth block for y, and the shapes of them are specified in that tuple to the right, the bm, bk, bk, bn, and then the output block is basically the result of that accumulation and will be the ijth block, and that'll be as bm, bn. And the idea here is that this is like the minimal amount of information you need to specify for us to automatically pipeline your kernel for you. Note that we haven't like specified anything about like how to prefetch or anything like that. We haven't like really talked about anything asynchronous. It turns out that with this minimal set of information, we can generate a pipeline automatically. And that's basically how you can get good performance on TPUs using Pallas. We write these block specs, we use a grid, and we pick the block sizes such that we hopefully are always compute bound. The trade-off is basically for a matmul, for example, is that the bigger the blocks, the more compute we have inside of the kernel, and the more time it'll take to execute one instance of the kernel, and therefore the more time we'll have to hide all the memory transfers. Smaller blocks means that, like, basically in a matmul, the compute scales essentially cubically with the block sizes, but only the memory usage only scales quadratically. So as we push the block sizes bigger and bigger, you get essentially more and more compute bound. So it's about finding kind of like a sweet spot there. Eventually you'll run out of VMem, or your pipeline bubbles will get really big. So this is something, yeah, I think I saw a question that's like, sorry, let me pull up the chat.
So do devs often need to iterate to find the right block sizes to optimize MFU? Yeah,
so certainly, like, with advanced knowledge about the TPU, you can kind of come up with heuristics that get you pretty good utilization. In practice, you're going to squeeze out every little bit of utilization you would sweep over a lot of block sizes and profile and collect timings, and that will tell you the best thing. This is something that XLA TPU does for you automatically. So basically, block size selection is something you have to do by hand in Pallas, whether it be via heuristic or just brute force. And it is very important for performance.
If I could ask a couple questions about this code, we haven't seen anything about num scalar prefetch or scratch shapes. Maybe you could give us a couple hints about what those mean.
So num scalar prefetch we'll get to later,
Okay.
and that has to do with SMEM. It's kind of there's a little bit of foreshadowing, if you will. Scratch shapes is basically like previously we would have this out shape, and that would construct this zref, but we might want something in vmem that's just existing for the lifetime of this kernel. So scratch shapes basically says allocate me this amount of vmem, and it'll be discarded once the kernel is done. The X, Y, and Z ref are kind of allocated automatically for you because you're passing in inputs from HBM and you want an output in HBM. So we'll create the corresponding scratch spaces for you. But if you want an additional one, you can allocate it via scratch shapes.
So scratch shapes, just to make sure I understand, corresponds to the output.
Scratch shapes has nothing to do with inputs or outputs. It's basically like, give me a fresh buffer in vmem that I'll only need for this kernel, and then it'll be gone.
Oh, the size of one block. Yeah, I see.
Yes. So that's specifically like the way this kernel is written such that we like accumulate. We could accumulate in a different D type, for example, than we store at the end.
But it corresponds to ACC underscore ref.
Yes.
Code?
Yes.
Okay,
ACC ref is the scratch here.
All right, perfect. And then one other thing, just too quickly before Metal gets in, this really connects to the conversation we had last week about accumulation and multiplication, where there's been a little bit of indirection, if I understand correctly here, to always accumulate the ACC refs, I guess it's the accumulation reference, in float 32, and then you're able to choose your preferred output spec.
Yes, there's some subtlety in writing a good, like a performant matmul on TPU. You want to get completely compute bound, you want to make sure you're copying your data in a like BF16 ideally, and then accumulating in F32 because that's how the matmul operation works on TPU. It outputs F32, and then copying back in BF16. So you do like a final downcast after you're done accumulating, and that's usually what matmuls on TPU do.
Perfect, and that's what we see the last line, is that downcast.
Yes, that last line is the downcast.
Perfect, thank you.
Your question?
Yeah, I have a question. So in terms of like tuning the block sizes, right? Like, of course, it would be D type specific. And like if you have quantization, then int8, BF16, FP32. But is it also anywhere like accelerator specific as well, or similar across?
Yeah, it can be as specific as, everything is a factor in this basically. I mean, once you have, as you said, it's like the D types, the shapes, the block sizes, the accelerator generation. You have to think about megacore as well. These are things that are all part of the equation in tuning.
So is there any tool which does this, or is it something that we do manually, like kind of?
Thus far, it's something we're doing manually, but like tools are in the works. It is, at least we use like XProf to do this kind of thing, to measure the timings and then read the results, and that'll give us like precise measurements on how long things take, and then these are logged and we can use that basically. That's generally how we do it. So yeah, I mean, I kind of hinted a lot of these things, but the idea here is that Pallas is like very closely tied to Jax. We use the same Jax representation, which allows things like VMAP. I think that's really neat. You can take a kernel like this and just VMAP it, and it'll work, which I think is really good, and it'll be performant as well. But some other cool things are that because we're in Jax, we can now do things like templating. I have an example later if we get to it to show just like a really simple metaprogramming example. Another cool thing though is that for most Pallas kernels, you can use what we call interpret mode, which is us emulating the execution using HLO. And it mimics the numerics of it and kind of the like order of execution of it, so that you can use standard Jax debugging tools when writing your kernels and debugging your kernels. And I think that's like a nice benefit of having a representation that's like shared in Jax when you write Pallas kernels. So that's kind of like the Pallas 101, if you will. This is now going into 102. So you guys, this is moving very quickly. But yeah, any last questions about like the 101? Yes.
So how performant are the so this matmul, for example, versus the one that exists now, what I assume is written in something lower level?
Basically, if given sufficient, like given the right block sizes, you should be able to match XLA's performance. That's the intuition. Like
Cool.
XLA selects block sizes extremely well. So often what we can do is we can compile a similar kernel and look at the block sizes XLA selected and use them ourselves. That doesn't always work, but at least for a matmul, if you just want to match it, that's something you could do. Cool. So in practice, oh, sorry. Do you have a heuristic on when to use the escape hatch versus trust the compiler to do the right thing? Yeah, good question. For something like a matmul, I would not use Pallas. Usually you will kind of know when you need, like ideally you can profile extensively and understand when the compiler is doing something wrong, or at least when it's not utilizing the TPU as well as it could. So there's kind of two reasons. There's two instances. One is you can look at profiles, see like, okay, yeah, I should be hitting this amount of utilization, but I'm only hitting this. And that can happen. And the other, which is a lot more common, has to do with this dynamic computation part that I'm going to talk about, where you're trying to do things that the compiler is just not able to do, or it's not able to do remotely efficiently. And this is kind of more along the lines of where Pallas is being used.
Or cases where the algorithm that the compiler knows about isn't very good. For example, flash attention.
Yeah,
is a third case. We talked about the algorithms for flash attention. The compiler doesn't know how to do those algorithms, especially in the backwards pass. So it can be helpful to use a handwritten Pallas kernel.
Yep. So dynamic computation is kind of like the one of the main things I want to talk about, which is kind of the frontier of what we're doing with Pallas. And the first thing we can do is if you remember that cartoon where we had this scalar memory and scalar registers, you can imagine alongside all this vector compute we have is a simple CPU that has just like it can do control flow, it can do scalar math, it can do some basic scalar computations, and it has registers, but it just can't do anything with the vector. It can't do anything with vectors. And you can imagine with that in mind what a TPU is actually capable of. You can imagine that while you're doing, like before you kick off a copy from HBM to VMM, you could do a cheap little scalar computation, and it actually tells you, instead of fetching this block, I can fetch another block. And what this allows you to do is you can do a lot of kind of data-dependent memory schedules. So previously with that grid and the matmul, we kind of have a fixed predetermined schedule of what our memory copies will be, and they're determined by the grid and the index maps. But we can generalize this using essentially values that are already in scalar memory. And that's why it's called scalar prefetch. The idea is that before you kick off your pipeline, you spend a tiny bit of time copying something from HBM into SMEM, and those values in SMEM can be used to determine what values you fetch in the pipeline and what compute you don't and actually do. So in this case, you can see that we passed in num scalar prefetch equals 1. And what that tells us is that this S value will be specially treated, and it'll be fetched into SMEM as opposed to pipelined into VMEM like X is. And because S is fetched into SMEM before the pipeline kicks off, we can refer to it in these index map functions. And not only can we refer to it, we can index into it and read its value. So you can see here that before, when we would just return ij or jk, we're actually doing an SMEM load operation into an sreg, and that scalar is used to tell the pipeline which block it's fetching. So in this example, I kind of have a bunch of like individual random values in this array, and I have this like 64 by 128 array that I'm carving up into 8 by 128 blocks, basically. And this S will tell us which blocks are fetched kind of randomly from this array. So this is kind of like a gather, and this is actually how gathers are implemented on TPU. You would prefetch kind of the indices into SMEM, and then kick off a pipeline that essentially does more random-like access into an array. And other than that, it looks like your regular old Pallas kernel, where here we're just doing a basic copy. So you can imagine this is like a really simple gather kernel. And the idea here is that we're actually doing dynamic memory access with a runtime value. And this is kind of one of the first things we implemented to unlock more data-dependent computation. Any questions about this?
Why is X transform returning us the 0?
It's a 2D block. So in this case, we're kind of, it corresponds to 128 dimension in X, and our block size is 128. So we're just returning like the only block, aka the 0 of the block.
The 0, I did 2D, yeah, I see.
Yeah. Cool. So the kind of main, like one of the main kernels that was enabled by this mechanism specifically is what we call splash attention, aka sparse flash attention. And this is essentially the most advanced attention kernel we have written. And it's advanced not because it's doing anything crazier than flash attention. It's advanced because it's actually kind of like a kernel generator. The idea is that you give it a NumPy mask, like the causal one on the left or the local one on the right. And because it's NumPy, it's static, we can pre-process it and construct a bunch of little data structures. And these data structures can be prefetched into SMEM, and they can be used to create essentially a pipeline schedule for that particular mask. So in the causal case, you can imagine a pipeline schedule where we do compute for this block here, but then we start prefetching the block in the next row, essentially. Like we can kind of figure out that we can skip this by staring at the mask and processing the mask. But the same logic can be applied to this. So we don't need to create a bespoke local attention kernel. We can just pass in a different NumPy mask and we'll generate an efficient pipeline schedule for this. And you can generate whatever mask you want, and it will cook up a pipeline schedule for it just by this ahead of time pre-processing. And this is basically how the splash attention kernel works. It's just doing some pre-processing, passing things into SMEM, and then SMEM is just telling us what blocks to do compute on and copy and which ones to not. Another kernel that is a little bit newer is what we're calling like the megablocks grouped matmul kernel. The idea here is that we're doing a matmul or a grouped matmul, and the idea here is that we have data that is essentially partitioned into groups. You can imagine this is our like activations or something. Then we have a set of weights, a group of weights. So we have the number of partitions of our data equals the number of weights we have, and we basically want to like select out just the activations that are assigned to each group in matmul with just that with its corresponding group. And you can imagine why this is like not super simple to express in Jax, because the way that this might be partitioned is extremely variable. All of them could be assigned to group 0, or could be perfectly uniform, and you kind of need to handle both cases. And it's largely determined by this like group sizes array, which is usually computed on the fly. It's like a Jax value produced by like a router and an MOE or something like that. So essentially what we can do is do some pre-processing on this group sizes in Jax, pass those things into SMEM, and construct a schedule that basically looks like this, where in the first iteration, we process that block, but we mask out the part that's in 6. We then process that same block again, but mask out the parts that are in the 3 group. We then move on to this block. We then move on to this block, process the only parts that are in the 6 group, and mask out the 8. Again, like kind of flip to the other one, process this one, process this one, process this one. So this schedule can be cooked up via this like make group metadata function, which is it's like a pure Jax function, returns a bunch of information, essentially like these small arrays containing metadata, and then these are then passed via scalar prefetch into the kernel, so we can essentially pick what groups to load every iteration of our pipeline. And this is how essentially the group matmul in megablocks works. So it's cool that like this very simple mechanism can enable this kind of dynamic computation. Any questions about that? Another aspect, and this is a bit more of an experimental feature, and it is actually used in the MegaBlocks kernels. Previously, grids were basically these static, iteration spaces. If you have a 2x2 grid, you're going to have 4 iterations, and it's always going to be 4. But now you can essentially pass in a runtime value, and that can be used to parameterize the grid. So you can imagine this could be used to early stop or something in a kernel. Maybe you're doing attention and you only have to process 10 or 400 tokens. You can devise a kernel that basically only loops up to that and stops, and you're done after that. So another cool mechanism we've added to Pallas recently to do early stopping. And this is like Pallas 103, and these are the really bleeding edge features, and it's control over memory copying directly. I'll pause now for any questions about all the scalar stuff. Yes.
Yeah, I have a question about that dynamic grid. Is that grid meaning like the block size you previously mentioned, or a different thing?
It's the block sizes will remain the same. The index maps will remain the same, but it'll just the number of iterations in the loop can be determined by a runtime value. Like the grid corresponds to a loop, basically.
Okay, in this case, do we still tuning the tiling size, or?
Yeah, in general, yeah, you'd always want to tune those.
Okay, so basically those are the 2 things. Okay.
Yeah.
Okay. Thanks.
So previously, I've been describing essentially this pipeline that's created automatically for you via these block specs and grid, and extensions to that. You can do a little bit of scalar prefetch, or you can have a dynamic grid. And these are ways of introducing dynamic computation into the existing auto pipelining, if you will. These are APIs that essentially let you implement that from scratch, essentially the pipeline emitter, if you will. And they're a lot more low level, but they've become important for essentially 2 reasons. The first is if you want to do like very fancy things with how you're fetching information from HBM into VMEM, for example, like dynamic sized DMAs. The one limitation of the old API is that you specify these block shapes, and the block shapes are static. They need to be known ahead of time and tuned. In general, the API does not require that, the lower level APIs. So here we actually give you the ability to fetch dynamic amounts of information in these copies. And another is asynchronous memory copying into other devices. And this is essentially the low level primitive, if you will, that's used to implement collectives in XLA, and that is also exposed. So we'll get to that in a second. But first, the basic primitive we give you is something called async copy. The idea here is that because these are asynchronous operations, we need some mechanism of synchronizing things, essentially blocking on those copies. And we expose semaphores essentially to the user. And you can allocate the semaphores via that scratch shapes mechanism before, or you can allocate them via this run scoped, where you call a body and it'll like give you a semaphore that's been allocated for you. And then the semaphore needs to be passed into these async copy operations. And then when you call .wait, it basically, the async copying will be happening essentially in a different thread, if you will. Or in the hardware, it'll be happening in parallel. And then in our current thread, which is actually running the kernel, we'll eventually want to block and wait until it's done. And the idea is that while you're copying, you can do whatever else you want. And that's how literally you are overlapping compute and memory copying is via this API, because it's done asynchronously. So this is kind of a low-level API that is provided. And you can see that you can not only copy like one array to another array. So here we're doing like HBM to VMEM, but you can copy slices of it. So you can say like .@0 and copy that into this slice of Y, and .@1 and copy into this slice of Y. And that's essentially how you can imagine like the block specs are used. You can imagine that we have one X that lives in HBM, and the block specs pick like a certain slice of it that we're copying into VMEM. And that's the API that is essentially used to do that. Yeah. And using that, we've actually implemented our own pipeline emitter. So you had Pallas call before, but now you could imagine we do a Pallas call where we don't use the block specs on the outside, but we use it kind of inside. So you can imagine us passing HBM refs directly instead of VMem refs into the kernel. And then we call this thing that looks a lot like Pallas call, very suspicious, but it's actually all Pallas essentially. It just emits raw Pallas using these async copy APIs. And you can imagine us implementing a far more flexible and extendable pipeline emitter using this API directly, because we don't have to go down into LLO to write the pipeline, but we can implement it ourselves in Python directly. So this emit pipeline is this like pretty, I mean, it's a very cool piece of code where we are basically writing this pipeline to describe to you explicitly in Python using Pallas APIs that I've already shown you. Other than that, it looks exactly like a Pallas call. And you might ask, why are we re-implementing pipeline emitter in Pallas? And there's basically two reasons. One is, as I alluded to, we can iterate on this far more quickly than we can on the LLO pipeline emitter, which is kind of like the XLA main emitter. This one is something that we can add a lot more features into it. For example, like more dynamic grid support, far more dynamic grid support. But another is that it composes really well with this API. And this is, as I said, the way you can do copying from one device to another device. And this is the mechanism by which all collectives are implemented in XLA. And we've exposed essentially the lowest level bit you can use, and that's async remote copy. And the idea here is that you again provide two refs, the kind of source ref and the target ref, but the target ref will actually be a ref on another device, and that's specified by a device ID. And you can see here that we are basically doing some like normal looking Jax thing where we compute our own access index, and then we add one to it, and that's getting our neighbor essentially to the right, if you will. And when you pass that into async remote copy and pass in a set of semaphores, we now essentially have two operations that we can block on. One is, are we done sending all that data? And in this case, we assume that someone will be sending us data, and that's kind of how XLA collectives work. Everyone's sending data and receiving data from someone else. So in this case, this receive done says, is someone done sending me data? And you can imagine you orchestrate this entire SPMD program where everyone's sending and receiving in a loop, and that will create something like an all gather or a reduce scatter or an all reduce, or this is basically something more like a collective permute. And these are the APIs that you'd use to actually do this. Any questions about this? I think this is like probably the most powerful mechanism we have in Pallas to this date.
So one thing we've been talking about a lot recently has been like ragged all-to-alls, ragged all gathers and reduce scatters for MOEs.
Yeah.
So I imagine this is the mechanism we'd want to use for that.
Yes, that's correct.
Pretty cool.
Yeah, so everything really boils down to those nice low-level APIs. Yeah, as I said, this is like, yeah, exactly what I said. Main only interesting detail is to ensure that you're kind of both at the same place in the program and your buffers are both ready to send and receive to. You want these like initial semaphores that make sure everybody's at the right place in the program. So yeah, so kind of like one of the cool things you can implement with this API and why, and it kind of justifies why we've written our own pipeline emitters, that you can write these big kernels where you have an outer loop that's sending data asynchronously and an inner loop that's kicking off these matmul pipelines. And that's basically how a collective matmul works. And you can see here, this is like an example that I wrote, and at least for this matmul, you can see that we're hiding the compute and we're hiding the comms of this all gather essentially pretty well using this matmul, using this custom collective matmul. This is something that actually can do, but it's kind of a compiler. It's not as flexible as the things you can do in the Pallas equivalent.
If I'm not wrong, is the performance better? It looks like even compared to the collective matmul we'd expect on the right, this thing on the left might be faster. I see fewer exposed all gathers than I remember in most collective matmuls.
Yeah, and it's there's a lot of like variables. You need to tune everything correctly, and depends on, you know, like there's a lot of optimizations you can apply that maybe I didn't here. But yes, in principle, you can match and maybe even do better than the XLA collective matmuls.
And better than handwritten shard map matmul.
which is essentially like what the XLA one would look like oftentimes.
I got it.
Yeah, like one optimization we can take advantage of in Pallas is that you can imagine in XLA when you write a collective matmul, you essentially write like a loop of collective permutes and dots. And the idea is that XLA will look at this loop and asynchronously schedule the collective permute for the next iteration in the current iteration. And very similar to like kind of like a Pallas call, if you will. The problem is that it's kind of happening at the HLO level. You can imagine we have a matmul, then a matmul, then a matmul, and each of those matmuls are their own independent pipelines. And as a result, they'll each have their own independent pipeline bubbles. So you can imagine in between the matmuls, you kind of have these bubbles where you're copying the result of the last step of the matmul back into HBM, and that's blocking. And then you have an initial blocking copy from HBM into VMem for the next matmul. But in principle, if you're chaining these matmuls together, you can actually kind of fuse them together as well and delete all these bubbles. And that's really hard to do at the HLO level because it basically involves fusing all these collective permutes and matmuls together into this one big magakernel. But the pipeline emitter that we've written that's entirely in Python actually has all these hooks in them where you can start fusing in the prefetch for the next matmul in the current matmul. And that's basically what you would like to do if you have really latency bound collective matmuls where this bubble time is non-trivial. So the idea here is that like in these latency bound ones, you can do even better because you have this additional opportunity to hide memory copying.
Super cool.
Yeah. That's basically all the slides I have. So we have like 5 minutes. I guess rather than diving into like some crazy live demos and overwhelming you with even more information, I think it's a good time to like collect questions and answer anything you're curious about. Thank you. Okay, so for Pallas 102, the strategy here seems to be use SMEM for scheduling, pipelining, directing, computation. Yeah, that's accurate. SMEM, you can think of like the scalar compute unit, if you will, as kind of orchestrating the vector compute unit and all the memory copying, and that's how it works. Yeah.
Could you go through some of the, or just briefly, or some of the issues I've been facing with Pallas are kind of cryptic errors or not sure exactly where the heart of it lies? And I didn't know if you had any pointers for stuff like that or any advice.
Yeah, that's a general theme of Pallas usage. It's experimental. And it's not very well, I mean, there's not a lot of people working on it. It's basically me and like 1.5 other people on the Jax team. And Mosaic is like 2.5 people maybe. So not a lot of people are working on this. And as a result, we don't have very helpful error messages. And there's kind of a well-trodden line you can follow to write kernels. But if you kind of deviate away from this, you're often going to hit these uninformative or tricky to debug issues. So Pate, I think, is referring to is one thing that often comes up is I described that Mosaic is this compiler that figures out how to take your like weirdly sized computation and tile it up over a bunch of fixed size registers. And it often doesn't have a lot of things implemented. You could imagine like there might be a computation that involves shuffling things around within a register or relaying things out across registers. And a lot of these cases are often unimplemented. So that's often one source of trouble, is just kind of unimplemented cases in Mosaic. And these are kind of being fleshed out over time. But certainly like there is a well-trodden path in which we know Mosaic works really well. Others are often like basically synchronization issues. We've exposed these low-level APIs that basically allow you to write this like parallel code, concurrent code. And as a result, you need to be very careful about synchronization and race conditions. And it's kind of hard to debug when you have those in your code because it leads to non-determinism and memory corruption and all sorts of crazy effects. So I think, at least in my mind, those are kind of the two main class of Pallas issues that a lot of people run into. I'm not sure if those, if your issues fall into either of those categories. but like we have ideas on how to improve them. They just take some time.
Yeah, I think at this point I've encountered a small collection, so I think that some fall into those camps for sure, but not all of them.
Yeah.
Or they may, and I just may not realize it.
Yeah, there's certainly a lot of sharp edges in Pallas.
So do you have any recommendations for like how to, because I don't want to constantly bombard the 3 people working on it.
I think that's fine.
Okay.
It helps us prioritize, and I mean, certainly, like, while there's a lot of like, there's go/Pallas chat, Pallas-chat, which is like the main chat room for this kind of stuff, and usually it's pretty active, and people in XLA TPU tend to be helpful as well. And yeah, I think it's perfectly within your rights to bother everybody in that chat because we don't really have anything else.
Okay, sounds good.
Cool. Well, I think no more questions. Thank you, everyone. It's been wonderful teaching this class, and thank you, Sharad, for joining us.
Yeah. Anytime. Thank you for inviting.
Thanks, everyone.
Thank you.